So let us see the important points. Okay. In fact, everything is important, but let us revise the chapter first, class crystal structure. So crystal structure, the important points are your packing efficiency, okay, packing density or packing efficiency. Then you have same packing density in plane, which we call planar density of atom. Okay, so we also calculated the linear density of atom. Okay, what is the density across in any direction? Okay, so that you have to revise, and then of course you have Miller indices. Okay, then you should know about the how to write the Miller indices of planes, how to draw the planes, and then of course you have what axial diffraction or reciprocal lattice first. Reciprocal lattice. Then you have axial diffraction. Okay, and then along with axial diffraction, you should have some information about neutron diffraction also. Neutron diffractions. Okay, so these are the these are the topics which you have to revise. Okay, of course you should know the formula for interplanar distance also. Okay, so interplanar distances. Okay, so let us take these topics one by one. So first of all, okay, let me start with the crystal. Okay, what is crystal? Okay, so crystal is basically your lattice plus basis. Okay, and basis meaning here is group of atoms. Okay, now all the crystals, okay, exist in the world, okay, can be classified. These crystals can be classified based on their lattice. Okay, so there are in two, if you with 3D crystal, we have total 14 Bravais lattices. Okay, so in 3D we have a 14 Bravais lattices. And again these 14 Bravais lattices can be classified in 7 crystal systems. Okay, and these 7 crystal systems are, you know, cubic, then tetragonal, then orthorhombic,
rhombohedral or trigonal,
rhombohedral, then then fifth one is hexagonal. Very good. Hexagonal, then
monoclinic,
monoclinic, and the 7th is your triclinic. Okay, so these are the 7 crystal systems. Okay, and also you should know which kind of unit cell exists in which kind of crystal system. For example, here the cubic system, your unit cell or Bravais lattice can be primitive cubic, okay, then it can be I also, body centered I. Okay, primitive, P at P, I for body centered, and F for F centered. 3 type of Bravais lattice exist in cubic system. In tetragonal we have only P and I. Okay, And in orthorhombic, we exist all the 4 type of unit cell: primitive, body centered, face centered, and one more is base centered also exists. Okay, so all the 4 exist in the orthorhombic. In rhombohedral you have only primitive type. Hexagonal you have only primitive type. Okay, then monoclinic you have primitive as well as body centered, and triclinic you have already primitive types. Okay, so total 1 2 3 4 5 6 7 8 9 10 11 12 13 14. Okay, we have a 14 type of Brevis lattices. Same thing if we talk in 2D. Okay, in 2D we have a 5 Brevis lattices. Okay, and these 5 Brevis lattices can be classified in 4 crystal systems. Okay, what are these 5 Brevis lattices in 2D? Tell me. What are the 5 Brevis lattices in 2D?
Oblique,
Oblique,
rectangular primitive,
rectangular, primitive,
rectangular centered, square, hexagonal.
okay, rectangular, centered, then
Square
square, very good,
and hexagonal.
and last is hexagonal. Okay, so these are the 5 Brevis lattices in 2D. Okay, now you have to revise these things. Now packing efficiency. So these are the, now let me write what is the packing efficiency. Okay, so packing density or packing efficiency, okay, is defined as number, what is the definition? Volume occupied. What is the definition of packing efficiency? Tell me how to define packing efficiency. Packing efficiency says how packed your structure is there. Okay, that means if you have some volume, how much volume is contained by the atom or molecules. Okay, that will tell you how densely that structure is packed. Okay, so volume of atoms or molecules divided by volume of unit cell. Okay, volume of unit cell. Okay, for example, if I say cubic, primitive cubic, okay, simple cubic. So simple cubic, you have n effective, okay, volume of atoms. Okay, so first you have to find how many atoms are there in the system. Okay, so simple cubic you have n effective is 1. The volume of the one atom is 4/3 pi r cube. Okay, and the volume of unit cell, so volume of one atom, assuming the atoms are spherical, volume of atom, okay, then volume of unit cell is a cube. Okay, and the packing efficiency will be your 1 into 4/3 pi r cube upon a cube. And in these kind of systems, you should always remember the relation between the radius of atom and the lattice constant. For example, here in cubic system, you have A equals to 2r, and if you put, when you solve this one, you get the packing efficiency is equal to pi by 6. Okay, if you put this one, you get pi by 6. For example, here you have a 1 into 4/3 pi r cube and A equals to 2r, so 8r cube, cancel. Okay, 1, and this comes out 2, so pi by 6. So this is simple cubic, it's pi by 6. Similarly, you have to remember this relation for different kind of unit cell or different unit cells. Okay, for example, if I have a FCC or BCC, Okay. So BCC, you have N effective equals to 2. Okay. Because ball atom is also in the center. So if you calculate the packing efficiency for BCC, what will be the relation? It will be 2 atoms N effective, and this will be the volume of atom, and then will be A cube. Now you should remember what is the relation between A and R in the BCC. So you know in the BCC you have one atom is sitting here also. Okay. So when one atom sitting here also, then tell me what is the relation between A and, so this is your A, this become your root A. Okay, and if this is the A, so what will this from here to here? What is the distance? This is distance root 3A. Okay, so your root 3A is equals to 4R for your BCC. Am I correct? Is that a correct relation?
Yes, sir.
Yes, sir.
So root 3A is equals to 4R for BCC. Okay, so that relation you should remember, that is your A is equal to 4 upon root 3R. Okay, and when you put this value here, your packing efficiency will come out. Okay, root 3 8 upon pi. Okay, which is equals to 0.68. Okay, similarly if you say FCC, okay, now for FCC your N effective is 4. Okay, N effective is 4, and FCC you have atoms at the plane. Okay, and we know for FCC the what is the relation? Root 2 equals to what? 4R. Is that the correct relation for A equals to what will come? 2 root 2R for FCC. Okay, so I think this should be the correct value, and if you put this value here in formula, okay, what you'll get? Atomic packing efficiency or atomic packing factor. Okay, you'll get the value is equals to pi 3 root 2, which is equal to 0.74%. Okay. Now tell me, what about the NaCl structure? Okay. If I take NaCl structure, in NaCl structure, what is the N effective for NaCl? NaCl, okay. So I want to find atomic packing fraction for NaCl. Can anyone tell me what is the value of N effective? Radhika, what is N effective for?
4, sir.
4. Okay, 4 molecule. Okay, or you can take, so 4 molecule of NaCl. 4 molecule of NaCl, or you can write 4 N plus 1 atoms plus 4 Cl minus 1 atoms. Okay, so if you want to now calculate the packing efficiency, what you will write? You write 4 into 4 by 3 pi R radius of sodium atom plus 4 into 4 by 3 pi R radius of chlorine atom. Okay, and divide by A cube. And for NaCl crystal, you know the relation between A and R is equals to 2. What is the relation? Tell me. Na plus
Cl minus RCl minus.
RCl minus. Okay, because now you have atom at the edges also. Okay, So if you have this kind of system, NaCl, okay, so you have, suppose sodium is at edges, here you have a chlorine. This edge is equals to 2, this edge is equals to A, okay, and this edge is equals to what now? 1 and 2, the twice of radius of sodium plus twice of radius of chlorine, okay. So you have a this kind of system. Here this is radius of chlorine, and here you have a diameter of sodium, okay. So you can write the relation between A and this one. Now you can put the values, okay, whatever the, you can put this value here, and whatever the values given in the question, radius of sodium and chlorine you can put, and you can calculate the atomic packing fraction for chlorine, okay. Similarly, if I take now diamond structure, okay, and diamond structure, okay, what is N effective in diamond structure? Tell me. What's the value of N effective in diamond structure? So N effective in diamond
Eight.
structure 8. Okay. And the relation between A and R. So A is given by 8R upon root 3. Okay. So basically, what is the relation between A and R? Okay. So one atom is at origin. So one atom is at origin 0, 0, 0, and another atom, another carbon atom is at a point P, which coordinates are 1 by 4, 1 by 4, 1 by 4. Okay, so two atoms are touching each other. Okay, and their center, say this is O atom as origin, and this atom is P. So this is 2. This is 2R, and 2R. So this is A by 4, A by 4, A by 4. So your 2R is equals to under root A by 4 minus 0 square plus A by 4 minus 0 square plus A by 4 minus 0 square. This is the distance formula. And if you solve this one, this will give you 2R. Okay. So 3, so root 3A. Okay. So you have a total 3 under root 3A square and 16. Okay, 16. And if you solve this one, this will give you root 3A upon 8A. Okay, 2R. Am I right or wrong? Any mistake here? So this is 3A square by 4 here, 4. 16, 4. Okay, so your A will be your 8R upon root 3. Okay, so this relation is important. This relation you should remember for different systems. Okay, so this is for diamond. A is equal to 8R upon root 3. Okay, once you know this one, you can calculate easily the atomic packing fraction. Okay, so atomic packing fraction for diamond is APF. That will be your 8 atoms inside, 4 by 3 pi R cube A cube. Okay, which is 8R root 3 by cube. Okay, and if you solve this one, this will come out root 3. कितना आएगा बताओ? Root 3 pi upon
16.
Okay. The next is our density of crystal. Okay. Or density of crystal. Density of crystal. Okay. And density of crystal is equals to density of unit cell. Density of unit cell. Okay. And which can be calculated. Density, we can calculate how much mass is present. Okay, how much mass is present in the unit cell divided by volume of the unit cell. Okay, density is mass by volume. So it is basically mass by volume. So how much mass is present? Okay, how much atoms are present? So we should know N effective, and we should know the mass of each atom. How many atoms are present in the unit cell, and divide by volume. Okay, and we know the volume for cubic system is A cube. Okay, now if I calculate for cubic system, cubic crystal, density will be N effective M up by N cube. Okay, N effective A cube. If you don't know the mass of atom, you have given the atomic mass. Okay, so atomic mass or molecular weight. Here M can be atom or molecule also. Okay, so like in an NaCl, we have a molecule, 4 molecules. Okay, or you write 4 NaCl atoms or plus 4 chlorine atoms. So either you can replace also with molecule also. So here M is what? M is your mass of atoms. Okay, or mass of molecule. Okay, and if molecular weight is given or atomic weight is given, then you can replace this M with molecular weight divided by Avogadro number. And here from you can also find, if you know the density, we can also estimate the lattice constant of the cubic system also. Okay. Now this was in 3D. Same thing we have to do for 2D and 1D also. Okay. So what is closest packing? Tell me, what is closest packing? Closest circle packing. What is the closest circle packing? Okay, of course, I'm talking about 2D. If I bring the equal sizes of circles, okay, and pack them, what should be the efficiency, packing efficiency of closest circles? If I bring circles, okay, closest packing of circles. Tell me how to calculate. What is the closest packing in the closest packing? Cyan, if you bring circles, okay, closest packing of circles. So the unit cell will be what? You have seen the unit cell will be like hexagonal. Okay, where you will be having atoms here like this. So this will be your closest circle packing. If the side is A, hexagonal side is A, and where A is equals to your 2R. So if you want to calculate if you want to calculate atomic packing fraction of this circles, then you have to find how many circles are there or atoms are there in this hexagon. Okay, so area of these atoms, so this each corner atom will contribute 1/3. Okay, so if you calculate n effective, okay, total there are 6 atoms at the corner, 1 2, so 1 2 3 4 5 6, and this will contribute only 1/3. Okay, they will contribute only 1/3. So it's 1/3 plus 1 is at the center. So this will become total 3. So you have to write 3 pi r square, area of the circle, and area of hexagon of side A. What is the area of hexagon of side A? Tell me.
3√3/2 a square.
3√3 upon 2
A square.
a square. Very good. Okay. And these values you can put here. 3 into pi r square. 3 upon 3√2. A is your 2r. That is 4r square. Okay. So 3 cancel. Okay. 1 2 cancel. R square cancel. This comes out how much? Pi upon 2√3. Okay. Pi upon 2 into √3. And if you solve this one, this will come out 0.9906. 0.906. This is for closest circle packing in 2D. Okay. Now the next is your interplanetary distances. Okay. So if you write here, this will be your interplanar distances. Okay. So interplanar distances, you have DHKL. So DHKL will be your for orthorhombic systems. Okay. For orthorhombic system. Orthorhombic system. Okay. Your DHKL will be, what is the formula? Tell me. This will be for H square, A square plus K square, B square plus L square, C square. Okay. If it's an orthorhombic system, and for cubic, you can write A equal to B equal to C. Okay. Then you have orthorhombic, then you have what? Hexagonal system, hexagonal. Okay, hexagonal systems. For hexagonal system, you have A equal to B not equal to C. Okay. So, no, this is for what? Tetragonal. This is for tetragonal system. Tetragonal. Okay. So you can write. So this is orthorhombic. Orthorhombic means you have A not equal to B not equal to C. Okay. From here you can write for cubic also. You can write for tetragonal also. Okay. Now, what is the formula for hexagonal? Can anyone remember? What is the formula for hexagonal?
1 by square root of 4/3 h square plus hk by plus k square.
1 upon
Square root 4/3.
4/3.
4/3. This for hexagonal you were saying, na sir?
Hexagonal.
4/3 h square plus hk plus k square. H square plus hk plus k square.
H square plus K square, then
Plus hk in bracket.
plus HK
by A square
by A square
plus L square by C square.
plus L square by C square.
Yes.
Okay. Anyone else please confirm whether this is correct formula? Hexagonal system. Lakshmi, is that fine? Hexagonal. Okay. So you have to remember for hexagonal also. I don't remember exactly now, right now. Okay. So now the next, we have already seen the packing efficiency. Let us now see how to calculate the planar density. Planar density and linear density. Okay. So let us find now planar density. Planar density. Okay. So what is the formula for planar density? Tell me, what is the formula for planar density? Can anyone tell me what is the formula for planar density? So plane, how many atoms are at the plane? Okay, that we write delta HKL. Okay, and what is the formula for delta HKL? N effective into DHKL into volume. This is the formula for planar density. Or you should know N effective, and you are calculating density for which plane. For that, you should know the interplanar distance, and of course, V is the volume. For example, if I am calculating for simple cubic system, okay, and I am calculating the planar density of 100 plane. Okay, so I know in a simple cubic system your N effective is 1, and I am calculating D100, and volume is of course A cube, and DHKL is for cubic system is given by H square plus K square plus L square. So you have A, and now this is 100. Okay, so this will be 1 square plus 0 square plus 0 square. So this will be D100 will be equal to A. So you can put here A, and this is your A cube, and this is 1 upon A square. Okay, so this will be the atoms. Okay, atoms per unit area. So D100 will be 1 by A square. Okay, atoms per unit area. Now value of A will be given in the question. Okay, and you can now, if you want to find the packing efficiency, how can you find the packing efficiency?
One by A square into pi R square.
Very good.
R equal to A by 2.
So this is the atoms per unit area. Okay, atoms. This is the packing density. Okay, how many atoms are per unit area? Now I want packing efficiency. Okay, so packing efficiency, atomic packing efficiency. Okay, so you got this one. Okay, you got the atoms. Now so how many atoms are there? One by this one. Okay, so now atomic fraction will be your 1 by A square. That is your atoms per unit area. Okay, and what is the area? Pi R square. How do we calculate? Tell me what is the formula?
Putting R equal to A by 2. R
Okay.
square equal to A square by 4.
A equals to
Pi by 4. Yeah.
2R. Okay. So this will be your A 1 by A square pi. Okay. R is A by 2. Okay. So A square upon 4. So how much will come? Tell me. What is the answer?
5/4. That I have to calculate the value.
0.75. So this will come out 0.785. This is the atoms per unit area. Now I'm writing the volume of I'm writing the area of one atom. Okay, so it will give me atomic packing fraction. Now similarly, this is for 100 plane. Okay, this is for 100 plane. Similarly, if I calculate atomic fraction for 110 plane for simple cubic, okay, that will give me how much? If I calculate the atomic packing fraction for 100 plane, the n effective is still 1. Now you're writing D110 A cube. How much will come? Tell me. This will come A upon root 2 upon A cube. So this will give me what? 1 upon root 2, okay, A square, and you multiply by pi r square. Okay, again you have 1 upon 2 A square. This is pi r is equal to 2r. So this is your A by 2 A square upon 4. Okay, so this will give you atomic packing fraction for 110 plane. This should give you pi upon 4 root 2, and this comes out 0.56. And similarly, if you calculate for 100, okay, similarly if you calculate this for 111, okay, so 11 plane packing fraction of 11 plane will come out as 0.453. 0.453. Okay, that is an important result you have to remember. Then simple cubic, you have a highest packing. Okay, closest packing is along is on 100 plane. Okay, so 100 plane in simple cubic, 100 plane has closest packing. 100 plane has a closest packing. Similarly, you can do it for now for BCC and FCC. Okay, so you have to remember the results. Okay, if I take instead of simple cubic, now if I take BCC, so only the n effective will change. Okay, and tell me which plane has the closest packing in BCC? Tell me, BCC, which plane has the closest packing?
100 plane, sir.
This is simple cubic. BCC
110 plane.
110 plane. Okay, in BCC you have a 110 plane as the closest packing, and FCC. And
111.
FCC you have 111 plane as a closest packing, has closest packing, and FCC you have has a closest packing. So the formula is same. Okay, the density formula is same. HKL, only unit n effective upon volume into DHKL. Okay, for simple cubic is 1, BCC 2, and FCC 4. This is always A cube. You can write this formula. So easily you can calculate the planar density easily using this formula. Okay, no need to draw the plane and calculate the count the number of atoms and then calculate the area. That will consume your time, more time. Okay, directly use this formula and just multiply by this pi square. That will give you packing fraction of that particular atom, particular plane. The next is your linear density. Okay, ये क्लियर है कि इसको और करूं मैं? You remember the formula exactly? You can calculate for plane density for different crystals now. Okay, simple cubic, FCC, and BCC. Now, similarly, you can find now linear density also. Okay, what is the atoms across a line? Okay, linear density. Okay, tell me what is the formula for linear density?
Atoms and the length by the length of the line
Linear density is atoms
and the length.
atoms on the length divided by
The length of the line.
the length. Atom on the length. Okay, atom on the line. Okay, and the length of the line. Length of the line. Okay. Now, for example, if I take simple cubic, okay, this simple cubic. Okay, this say if I say this is x-axis, x, this is y, and this is z. Okay, then this direction is what? Tell me, what is this direction? This direction is what? 1, 0, 0. If I'm saying this is x-axis, so I want the linear density across this 1, 0, 0, 1, 0, 0 direction. So in 1, 0, 0 direction, you have how many atoms? Tell me. If this is 1, 0, 0 direction, okay. So the length is how? Length is how much? Length is A. And this length covers how many atoms? Half of this atom and half of this atom. So half atom plus half atom. That is total 1 atom. Okay. So this is 1 atom. 1 atom upon A. Okay. So this is basically atom per length. Okay. Now 1 atoms has a distance r. Okay. So now how much length 1 atom occupies? That is occupies 2r. 2r by A. Okay, 2r by A. So atom, so this is r and this is r. Okay, so the length occupied by is 2r. And now we know simple cubic, they atoms are touching to each other. In simple cubic, these atoms are touching to each other. So this is your what? This is your r. So your A equals to 2r. So if I put here A by A, that gives me 100%. Okay. So the packing efficiency of this 100 direction is 100% in simple cubic system. Okay. So this is the closest packing in 100 direction. Tell me now packing efficiency of 100 and 11 direction. Similarly, if I want now this is for 100. Similarly, if I want this 100, 110, and if I want say this across this line 111, okay, how to calculate? Tell me. In simple cubic, okay. So linear density along a 110 direction I want to find out. Okay, so how can I write? Tell me. So that will be again the length. What is this length? Tell me. What is this length? So number of atoms, okay, and the length. So this is that this length is your A, this length is A.
Root 2A.
Root 2A, na? Root 2A, okay. So length will be root 2A, and again there are 2 atoms. 2 atoms, half atom, okay, plus half atom. So why this is root 2a now? Why this is root 2a this time? We are calculating 100, no? So this is 100. So this is 100. Okay. So this is root 2a. So 1 atom upon root 2a. Okay. And 1 atom is again 2r. Now, but whether these atoms are okay. Now in cubic system, all these atoms are touching to each other. So again, you have 2r upon root 2a. Okay, 2r upon root 2a, and this is 2r root 2a is equals to 2r. So this is 1 by root 2. How much will come? Tell me. 0.707. And if similarly, if you want to find out now for 1 direction, tell me what will come 1 direction. What will be the length now? What will be the length?
Root 3a.
Root 3a. And it will be root 3a. Okay. And if you solve this one, this will come out your 1 by root 3. Okay, packing efficiency, and that will be 0.57. So this is for simple cubic. Similarly, now you can find out this for BCC also, same manner. Okay, BCC. So BCC is a closest packing along which direction? BCC. So simple cubic has closest packing along 100 direction, same like plane. Okay. Now, if we has a BCC, what is the closest packing direction for BCC?
111.
Very good. Now this is
Yes,
not
sir, 111.
now this is not 110. This is for packing the closest packing direction. Closest packing direction. Okay, for BCC is your either you say 1 bar 1 1, the family of 1 bar 1 1 1, or 1 1 1 1 also you can say. Okay. Similarly, for FCC, closest packing direction. Closest
110.
packing direction. Okay, the family of 1 1. Okay, 1 1 0. Okay, 1 bar 0, or you can simply write 1 1 0. Okay, so this was your densities. Okay, now the remaining is axial diffraction and neutron diffraction. Okay, that I think I will discuss tomorrow. So solid state physics mein, there is not only formulas. Okay, you have to remember the concepts. Okay, definitions. Those also important thing.
Sir, can you please explain that again? I have told you that why KCL structure that instead of having a FCC thing.
Tomorrow I'll discuss.
Okay, sir. Okay.
XRD I'll discuss tomorrow. Okay, so XRD and neutron diffraction I will discuss tomorrow. Okay, and with this thermal properties. So concept you should remember also. Definition, concept also you should remember. Facts, generally they ask facts. Okay, in solid state physics, they ask. Okay, they ask graphs like resistivity versus temperature graph, magnetization versus H graph. So they ask from dependence. Okay, the dependence of physical properties on some parameters. Like generally they ask then specific heat variation with temperature. What is the relation for 1D, 2D, 3D? What is the relation between how resistivity varies with temperature for metal, for semiconductors, okay, for semi metals? So those dependence formulas they generally ask. Okay, so we'll revise those things in coming classes. So I'm stopping here.
Thank you, sir.